All right. Hello, my name is Mia, and I'll be helping walk you through the Fall 2020 sample exam problem number 2, the reverse environment diagram. So, what is a reverse environment diagram? A reverse environment diagram is essentially, instead of us being given the code and having to fill in the environment diagram for it, we're given the full environment diagram, and we have to fill in the parts of code that result in the environment diagram. So, let's get started. All right, here is part A. Now, take a minute to look over that environment diagram. However, I'm going to jump straight into the code. All right, so let's walk through this as if we actually are making the environment diagram ourselves. So let's walk through it step by step. Okay, so we have the first line, def can tab, and we can see that we define it right up there. The function can takes in tab and its parent is global. Now we have the variable soda. What is soda equal to? Soda is equal to a lambda function on line 4. It makes it 1, 2, 3, 4. That takes in Coke. Why just this part and not the entire thing? Because you can see that lambda that takes in Coke is a higher order lambda, as in you can think of these lambda statements as def statements. So in a normal environment diagram, we'd really only care about this first little bit because that's what's actually defined in the global frame. The rest of this is yet to be defined, so we can just ignore it for now. Okay. Now we have, let's not really care about what this is for right now, so we can just ignore that. But let's move on to pop. What is pop equal to? Pop is equal to a call to soda, and then whatever soda returns, a call to that. Somehow, in our environment diagram, it evaluates to 4. So our end goal is for all of this to evaluate to 4. Okay, what is soda? We know soda, by checking our environment diagram, is equal to our function, our lambda, that takes in Coke on line 4. So we know that this frame 1 should be our lambda that takes in Coke. All right. Now, we know lambda takes in the value Coke. Let's check our environment diagram to see if that's given to us. And we can see it is. There's Coke right there. Coke is equivalent to 3. So this first call should be 3. Soda, 3, or our lambda with Coke equal to 3. All right. Again, because lambda Coke is a higher order function, it's going to return lambda Pepsi, as you can see in our environment diagram, on line 4 with parent F1, because that lambda was defined in our F1 frame, what we're working in right now. Okay, well, because this call evaluates to our lambda that takes in Pepsi, we're now calling the lambda that takes in Pepsi. So this right here is our Pepsi. Our second call is our Pepsi, which means this frame is again our lambda that takes in Pepsi. What is Pepsi? Let's check our environment diagram. Pepsi, oops. Pepsi looks to be a pointer to the function can with parent equal to global. So we can put can in the second call. All right, now we know somehow our lambda Pepsi ends up returning the numerical value 4. So this whole computation is going to end up returning 4. Well, we also know that we open up a new frame right here. So that means there has to be a new call. All right. So since we just passed in can as Pepsi, as in the function can as Pepsi, it would make a lot of sense to be using it right here. So we're using Pepsi, which in this case is can, our function can, and we probably want to call it because again, we open up this new frame and there's really no other appropriate place in the code that we'd be calling Pepsi, whatever Pepsi is equivalent to, or whatever, or just can. So we open up this new frame with this call, and our Pepsi, which is can, takes in tab. So what is tab in our environment diagram? We can see it's 3. Now, it would logically make sense to put 3 right here, but when you really think about it, 3 is a static or stagnant value, meaning that no matter what we pass in as Coke or Pepsi, or no matter what we pass in as Coke, do we always want Pepsi, whatever Pepsi is, to take in 3? It would be a little weird. So a good thing to check is there anywhere else in our code that is equivalent to 3 right now, as in this call? So we're doing this computation, this return value computation in frame 2. So is there anywhere in frame 2 that there's a variable equivalent to 3? It doesn't look like it. So let's check our parent frame, F1. So looking in F1, is there any variable equivalent to 3? Yeah, we have Coke equivalent to 3 at that time. So it would make sense to pass Coke into Pepsi. All right. Now, remember the end goal? We want this call, passing Coke into Pepsi, to be equivalent to 4. So passing 3 into can, well, it looks like it just increments it by 1. So it's as simple as doing tab plus 1. And that should be it for this problem. Let's move on to part B. All right, here is our environment diagram for part B. Maybe take a moment, look at it, and I'm going to jump straight into the code. All right, let's do exactly what we did before, going through it line by line as if we're making it ourselves. Okay, so we have def make school. Here we go, it's defined right there. And we have def find better school. Awesome, defined right there. Both of these with parent equal to global. And now we have the variable Berkeley. So Berkeley is a call to make school, and since it's our very first call, it means that this first frame, whatever it evaluates to, is probably what our Berkeley variable evaluates to. So what do we pass in? We pass in the string UC Berkeley as our name. Okay, that checks out. But we don't have our location or our coolness. So let's check the environment diagram. Okay, awesome. We're given a location, California, and and we're given a coolness 1,000. So let's fill those in. California and a coolness 1,000. Awesome. Okay, what does our make school return? Make school seems to return a dictionary. We can confirm this by looking at the hint as well. The hint says the dictionary found in the environment diagram refers to a dictionary instance. So make school has to make a dictionary. With these keys and these values. But we know that all of these values are the parameters or are the arguments that we pass into our parameters, as in name, location, and coolness. So let's make our dictionary in make school. We do a curly bracket. Then what's our first key? Our first key seems to be the string school name. And that should be set equal to our name variable, as you can see here. Our second key seems to be loc. And what is that set equal to? Our location, as you can see here. And our third key is coolness. The string coolness set to our coolness level, or the parameter. We finish it off with another set of curly brackets. Awesome. Now, let's do the same for Stanford, because it seems like we call make school again. So this is a second call to make school, so a second frame, which means the second frame, whatever it evaluates to, is probably what our Stanford variable evaluates to. All right, we can see that Stanford University is passed in. We don't have our location or our coolness. Let's look at the environment diagram to see if we have it. It looks like we do. We have our location, California, and our coolness, 0. So let's put in California. Let's put in 0 for our coolness. And we're at the last line. Okay, so we have our variable best school, which is equal to a call to find better school with our Berkeley dictionary and our Stanford dictionary passed in. So that means this last frame, whatever it evaluates to, is equivalent to our best school variable. Okay, school 1, we can see is Berkeley. So that's school 1. So that means school 2 is Stanford. You can also see that in the environment diagram. School 2 is Stanford. All right, and it seems to return UC Berkeley. Let's find out why it does that. Why does it return the name, the school name of our dictionary, Berkeley? Okay, so we have if school 1 coolness. Remember, school 1 is our Berkeley dictionary. And school 2 coolness. Remember, school 2 is Stanford. If the school 1 coolness is greater than school 2 coolness, we return, well, what would make this true? Well, this is kind of already true. Our school 1 is Berkeley, and we're trying to get the value at the key coolness. The value at the key coolness is our coolness level, which for Berkeley is 1,000, and for Stanford is 0. So that's true. So this return value right here is the true case, meaning that since this is true, we want to return the name of school 1. How do we get that name? We do our dictionary name, which is school 1, and we use the key school name to get our school name. Alright, so if that's not true, if the coolness of school 1 is not greater than the coolness of school 2, as in the flip case, let's say Berkeley was 0 and Stanford was 1,000, then we'd probably want to return the name of school 2, which we do in the same way we did for school 1. And that should be it for this problem.